Imagine standing on the surface of Mercury, not during the searing daylight, but under the pitch-black sky of its endless night. The sun has long vanished beyond the horizon, and it won't rise again for weeks. The stars above are sharp and unfiltered, the silence absolute. But you're not here just to survive. You've brought something special, a sensor pointed away from the sun, into the dark. And what it reveals is something astonishing. A ghostly tail, millions of kilometers long, stretches from Mercury into space. Not made of dust or ice, but of something stranger, sodium atoms. This isn't a comet. It's a planet, rocky, dry, and blistered by solar fury, trailing an invisible beacon through the void. This is Mercury's sodium tail, and it changes everything we thought we knew about the innermost world of our solar system. For centuries, Mercury was seen as a dead rock, devoid of atmosphere, activity, or surprises. But in 2001, astronomers at McDonald Observatory noticed a faint glow far beyond the planet's edge using special sodium filters. At first, they assumed an error. Instruments were recalibrated, data rechecked. But the glow was real. Mercury had a tail, a massive one, stretching 2.5 million kilometers, more than 700 times its own width. It had somehow gone unnoticed for decades. Comets have tails because they're icy. As they near the sun, that ice sublimates, creating a trail of gas and dust. But Mercury is a bone-dry, rocky world. Its tail forms not from melting, but from violent interactions with its environment. The solar wind, a relentless torrent of charged particles, slams into Mercury's surface at over 1 million kilometers per hour. These particles knock atoms loose in a process called sputtering. Think of magnets stuck to a fridge, and then imagine throwing a ball at them. Some fly off. That's what happens to atoms on Mercury's surface when struck by high-energy solar particles. The element most easily knocked free, sodium, and there's more. Because Mercury has almost no atmosphere, it's bombarded by micrometeoroids, tiny grains of space dust that hit with incredible force. These impacts vaporize material on contact, ejecting even more sodium into space. The space erosion, stripping the planet atom by atom, day by day. Once freed, sodium atoms don't just float nearby. They're pushed by sunlight itself. Photons may have no mass, but they carry momentum. When sodium atoms absorb photons, they get nudged again and again away from the sun. It's like each one is a miniature solar sail, drifting backward into space. This radiation pressure overcomes Mercury's weak gravity and sculpts the tail, always pointing directly away from the sun. But you can't see it with your eyes. Sodium glows at a precise wavelength, 589 nanometers, the same color as old yellow street lamps. To reveal the tail, astronomers block out every other wavelength using sodium filters. By deleting all the unwanted light, the sodium glow finally appears. Interestingly, Mercury's sodium tail doesn't shine at the same intensity throughout its orbit. You might expect it to peak when the planet is closest to the sun, but it actually becomes brightest 16 days later. Why? Doppler shift. After Mercury slingshots around the sun, it accelerates away at nearly 59 kilometers per second. This rapid movement causes the light from the sun to stretch, shifting its spectrum. Normally, sodium-specific light from the sun is absorbed by its own atmosphere. But thanks to the redshift, that light becomes available again, allowing the tail to absorb it and glow more intensely. Faster motion, stronger signal. However, spotting the tail from Earth isn't just about timing. The geometry has to be perfect. Mercury must be far enough from the sun's glare, not hidden behind it, and angled just right for telescopes to catch its tail. These alignments are rare, happening only every few years. That's what made the 2001 discovery so extraordinary. A lucky accident caught during a fleeting window of opportunity. But this isn't just about Mercury. It opens a window into planetary erosion, surface evolution, and even the nature of exoplanets. Over billions of years, Mercury's surface composition could shift as light elements like sodium are slowly stripped away. And if this small rocky planet can form such a tail, what might be happening on hot Jupiters, massive planets orbiting incredibly close to their stars? The same mechanisms could be at work on a much larger scale. In fact, we've already detected similar tails around our moon, suggesting that airless bodies exposed to solar wind may commonly shed material into space. Mercury's sodium tail has become a template, a way to study interactions between stars and planets near and far. And now, with ESA's Columbbo mission on its way to Mercury, we're on the brink of a new era of discovery. After multiple flybys, it will enter orbit in 2025 and observe Mercury for at least a year, gathering unprecedented data about its surface, exosphere, and mysterious tail. This strange, glowing trail reminds us of something crucial, that even our closest neighbors in the solar system still hold secrets. In the quiet, dark sky above Mercury, we found not just sodium atoms, but a new story about light, motion, erosion, and the unseen forces that shape worlds. The universe never stops surprising us. All we have to do is keep looking.